Yeah, the fifth unit of applied physics syllabus is nanotechnology. In nanotechnology, we have to study the first topic is nanoscale. That means in nanoscale, we have to study the basic definition of nanoscale and the different type of nanomaterials. And after that, we have to study various factors that affect the properties of nanomaterials. In that, we have to study two factors. One is the quantum confinement effect. Second one is surface area to volume ratio. These are the two factors affect the properties of nanomaterials. And after that factors, we have to study different synthesis mechanisms of nanoparticles. In the different synthesis mechanisms, we have to study two approaches. First one is the bottom-up application. Second one is the top-down fabrication. In bottom-up fabrication, we have to study Sol-Gel method and precipitation method. In top-down fabrication, we have to study three methods here. One is the ball milling. Second one is the physical vapor deposition. Third one is the chemical vapor deposition. These are the synthesis methods we have to study in our syllabus. Total, we are having five synthesis methods. Okay, and after synthesizing nanoparticles, we have to study their properties. For studying their properties, we are having three characterization techniques. One is the XRD, second one is the SEM, third one is the TEM. These are the three characterization techniques we have to study in this nanotechnology. And finally, we have to study the applications of nanomaterials. Okay, this is our syllabus of nanotechnology. Yeah, now we will start with the basic concept that is nanoscale. What is the meaning of nanoscale? Okay, first we have to study basic definition that is the nanoscale. See, first we have to study the basic definition of nanoscale. Here, how can we define this nanoscale? See, this nanoscale means we can say as the nanomaterials. These nanomaterials are those materials, okay, and which have one or more dimensions of the order of 100 nanometers or less. That means in any one of the dimension, the value should be 100 nanometers or less. Those materials we can call nanomaterials in any one dimension. Suppose if you material, we can take, we are having one dimensional material, two dimensional materials, three dimensional materials. Okay, in the dimensions, any one of the dimensions that is the order of 100 nanometers or less, those materials we can call nanomaterials. This is the definition of nanomaterials or nanoscale. Nanomaterials are defined as those materials which have one or more dimensions of the order of 100 nanometers or less. That means any one of the dimensions that should be 100 nanometers or less, those are called nanomaterials. Now we have to study different types of nanomaterials. Here we are having four types of nanomaterials. In that, first one is the zero dimensional. Okay, that means classification of nanomaterials. In that, first one is zero dimensional. Second one is the one dimensional. Third one two dimensional, and fourth one three dimensional. This is the classification of nanometers. We will study one by one. First one is the zero dimensional. Zero dimensional means these zero dimensional nanoparticles are spherical in shape or size, and the diameter of these particles will be in the range of 1 to 50 nanometers. That means these are the main requirement for zero dimensional. That means the particle are in the shape of spherical, and the diameter of these particles will be in the 1 to 50 nanometers range. Okay, those are the requirements for zero dimensional nanomaterials. Example we will take, that is gold nanoparticles. That means gold nanoparticles are best example for zero dimensional. What are the requirements for zero dimensional? The first one is the particles are in the shape of spherical or size in the shape of spherical, and the diameter of these particles will be in the 1 to 50 nanometers range. Those are called zero dimensional. Okay, that means these gold nanoparticles, the shape you can observe, that is spherical in shape, and if you observe the diameter, that is in between 1 to 50 nanometers. That is the zero dimensional. And the second one is the one dimensional nanomaterial. These one dimensional nanometer, these one dimensional nanometers are looking long. That means several micrometers in length, but with a diameter of only few nanometers. That means in one dimension, that is the nanoscale. That is the diameter. But lengthwise, if you observe, that is not a nanoscale. That is several micrometer in length, but diameter of only few nanometers. Those are one-dimensional nanometers. Best example is carbon nanotube. In these carbon nanotubes, if you observe, the length that is not in nanometer, but if you observe the diameter of this carbon nanotube, that is few nanometers. That is the example for one dimensional. That is carbon nanotube. And the next one is the two-dimensional. In two-dimensional nanometers, if you observe, okay, we are having different type of two-dimensional nanometers. These include different kind of nanofilms. Example, coatings and thin film multilayers, nanosheets, or nanowalls. These are the different type of two-dimensional nanometers. That is in the form of films. That means example we can take such as coatings, nanofilm multilayers, nanosheets, or nanowalls. If we observe the area of the nanofilms, that is large. That is not in nanoscale. That means several square micrometer, but thickness is always in nanoscale range. You can remember this. Okay, actually, in any one dimension, that should be nanoscale. If you observe in this two-dimension nanomaterials, okay, if two-dimension means that should not two directions in nanoscale. Here, the example is film. Okay, that looks like two-dimensional, but the nano size is thickness. The nano size is thickness. Example is solar thin film. That is the two-dimensional nanomaterials. And last one is the three-dimensional nanomaterials. Actually, how these three-dimensional nanomaterials will form? These include bulk materials composed of the individual blocks which are in nanometer scale. That means you can take the multiple nanomaterial, you can compose all those uh, individual blocks. Then bulk material will form. That is the example for three-dimensional nanomaterial. Okay, these three-dimensional nanomaterials will include the materials composed of the individual blocks. Okay, these are actually bulk materials. Three-dimensional means those are bulk materials that is composed of the individual blocks which are in nanometer scale. Okay, the range is 1 to 100 nanometers. Okay, these are the four types of nanometers. First one is the zero-dimensional. The requirement is the material is in the shape of spherical and the diameter is in nanometer range, that is 1 to 50 nanometers. If you observe one dimensional nanometer, the length is long actually, that is not in nano size. But if you observe the diameter, that is in nanometer range. Example, carbon nanotube. In two-dimensional, the area is large, but thickness is a nano range. In three-dimensional, these are the bulk materials. Those are composed of the individual blocks which are in nanometer scale. That is in 1 to 100 nanometers. These are the four types of nanometers. Next, we have to study various factors that affect the properties of nanomaterials. Here, mainly two factors that affect the properties of nanomaterials. That means if we decrease the particle size, the properties also changes. If you observe the best example, wheat flour. Okay, wheat flour, if you grind more, we will get the maida. Okay, that means both are coming from wheat only. Okay, if you observe the wheat flour and maida, both are coming from wheat flour. But if you observe the particle size, both are different. If you observe the properties of wheat flour and maida, entirely different. But even the initial material is same, that is the wheat. Okay, but if you observe if you decrease the particle size, the entire properties will change. Why the properties of the particles are changing? Why the properties of nanoparticles are different? Because of two factors. Two principal factors that cause the properties of nanometers to differ significantly from other materials. Okay, in that, what are those factors? First one is increase in surface area to volume ratio. Particularly in case of nanometers, surface area to volume ratio increases. Second factor is quantum confinement effect. Because of these two factors, the properties of nanometers will differ from the bulk materials or other materials. Okay, if you check these two one by one, first one is increase in surface area to volume ratio. Okay, because of these two factors, almost all the properties of nanoparticles will change. Example, I have given three properties here. One is the reactivity, that is chemical property; strength, that is the mechanical property; and electrical characteristics. Along with these, magnetic properties also changes, thermal properties also changes, optical properties also changes. That is because of these two factors. One is increase in surface area to volume ratio. Second one is the quantum confinement effect. Because of these two factors, all the properties of nanoparticles will change. Chemical property, mechanical property, electrical property, thermal property, magnetic property, optical property. All these properties will change for nanoparticles compared with the bulk materials because of these two factors. Now we will check one by one. What is first one? Increase in surface area to volume ratio. Okay. Generally, if you observe the nanoparticles, the surface area of these nanoparticles is relatively larger when compared to the same volume of the material produced in the larger form. Okay, the surface area of these nanoparticles are larger when we compare to the same volume of the material produced in larger form. See, if you observe this point, nanomaterials have a relatively larger surface area when compared to the same volume of the material produced in a larger form. So, for example, we will take these two examples I will explain here. One is for sphere, second one is for cube. First, if you observe sphere, okay, let us consider a sphere of radius smaller. Now we will calculate the surface area to volume ratio. For that, first we are calculating the surface area of the sphere. What is the formula? Surface area equal to 4 pi r square. This is the surface area of the sphere. Then what is the volume of the sphere? That is 4 by 3 pi r cube. Okay, these are the formulas for surface area and volume for sphere. Now we are going to calculate the surface area to volume ratio. Okay, if you after calculation, what we are getting? 3 by r. If you observe this formula, surface area to volume ratio equal to 3 by r. R is the radius of the sphere. That means if you reduce the R value, that means if you are decreasing the particle size. If you are reducing radius of the sphere, that means R value. If you are reducing, that means decreasing. The radius, the particle size means decreases. Okay, if the particle size decreases, surface area to volume ratio increases because both are inversely proportional. Surface area to volume ratio is inversely proportional to radius of the sphere. Thus, when the radius of the sphere decreases, its surface area to volume ratio increases. This is the example taken from sphere. Now we will study for cube. Okay, first we will consider cube here. Let us consider another example for 1 cubic volume. If you observe the surface area, that is 6m square. Formula is 6a square. 1 cubic volume is a equal to 1. Surface area is 6 meters square. Now what we are doing, this cube we are dividing into 8 pieces. Then we can calculate the surface area of the that 8 pieces and we can add. Okay, finally we are getting the 12 meters square. That means if it is in one piece, okay, 1 cubic volume, we are getting the surface area 6 meters square. When we are dividing into 8 pieces, the surface area becomes 12 meters square. Now same volume we are dividing into 27 pieces, its surface area becomes 18 meters square. That means if you observe the number of pieces increases, the surface area also increases. That means thus we find that when the given volume is dividing into smaller pieces, its surface area increases. Hence, as particle size decreases, its surface area increases. Example we will study. See, one piece, that means A equal to 1. Surface area formula 6 into 1 square 6 we are getting. Okay, if you are dividing into 8 pieces, that means the side of one piece is 1 by 2. Okay, now if you calculate 6 into formula is 6a squared. 6 into 1 by 2 whole square. A equal 1 by 2. Total how many pieces are there? 8 pieces. Then 8 into 6 into 1 by 2 whole square. Then you are getting the 12 meters square. Then we are dividing into 27 pieces. That means A equal to 1 by 3. So this 6 into 1 by 3 whole square into 27. We are getting the 18 meters square. That means we are increasing the number of pieces. The surface area increases here. Okay, this is the formula for surface area of the cube, that means 6a squared. That means these nanoparticles have a greater surface area per given volume compared with the larger particles. It makes materials more reactive because maximum chemical reactions happening on the surface of the particles. That means because of increasing surface area, it will be more reactive. Okay, as growth and catalytic chemical reactions also occur at the surfaces. That means maximum chemical reactions occur at the surfaces. That means that a given mass of material in nanostructure form will be much more reactive than same mass of the material made up of the larger particle. The reason is compared with the larger particle, nanoparticles having the more surface area. If there is more surface area, then more chemical reactivity is there. This affect their strength or electrical properties also. This all the properties that will affect. Okay, by decreasing particle size, that will affect all the particles. That is decreasing particle size, increasing surface area, that will affect the all the properties of the nanomaterials. Okay, this is the cube you are taking. 1 centimeter side, the surface area is 6 centimeters square. Now we are dividing into 8 pieces. The side is 0.5 centimeter. Then surface area is 12 centimeters square. This is about the increase in surface area to volume ratio. What is the second parameter? That is the quantum confinement effect. Okay, that we will study. If you decrease the particle size here, surface area increases. Now we will study second one, that is the quantum confinement effect. Okay, in this quantum confinement effect, what is the exact meaning of quantum confinement effect? Okay, here particularly the electron levels changes. When the electron levels changes, we will check here. Okay, here if you observe the first point, if we are taking the atoms are isolated, the energy levels are discrete. For example, we are taking 10 atoms. The 10 atoms having 10 different energy levels. That means when atoms are isolated, the energy levels are discrete. Now what we are doing, when very large number of atoms are closely packed, the 10 atoms we are packing, that will form a solid. Then what about the energy level? That energy levels are split and form the bands. Okay, individual isolated atoms are, if you observe the isolated atoms, the energy levels are discrete. When we are combining all the isolated atoms, that will form a solid. In that case, the energy level split and form the bands. But in case of nanomaterials, that represents the intermediate stage, not in isolate, not in discrete, or not form the bands. Second point is the okay. In quantum mechanics, already we have studied the particle in potential well or potential box. Okay, we have studied the problems of particles in a potential well as well as in a potential box. These potential well or box dimensions is in the order of de Broglie wavelength of electrons. The energy levels of electrons change. That means here we are taking the dimensions of such potential boxes or wells are of the order of de Broglie wavelength of electrons. That means this potential box dimension is of the order of de Broglie wavelength of electron. In that case, what is happening? Energy levels of electrons change. This change in energy level of electrons is this effect we can call quantum confinement. Okay. Next. Now we are decreasing particle size 10 nanometers or less. That means when the material is in sufficiently small size, typically 10 nanometers or less, organization of energy levels into which electrons can climb or fall change. That means when we are decreasing the particle size up to 10 nanometers or less, automatically the energy levels of electrons reorganize. That means the electron can climb or fall change. Due to that, energy levels are reorganized. Especially the phenomenon results from electrons and holes being squeezed. You can take one electron and hole and you can squeeze that one. Then that is converting into a dimension that approaches a critical quantum measurement. That is called electron Bohr radius, exciton Bohr radius. That means you can take one electron on a hole and you can squeeze that one. Whatever dimension we are getting, that is critical quantum measurement. That is called exciton Bohr radius. Because of this quantum confinement effect, that will affect the optical, electrical, and magnetic behavior of the materials, particularly as the structure particles approaches the smaller end of the nanoscale. That means we are decreasing particle size, all these properties changing. Okay, just you can observe this one. See here, this we are decreasing the particle size. If you observe, these are the looking like balls. The diameter is decreasing. That means the particle size is decreasing. Then what about the energy gap? Okay, in case of this red color ball, if you observe the energy gap, that is smaller. Okay, you can decrease the particle size, yellow color, green color, blue color balls. That means you are decreasing the particle size. If you observe the energy gap is gradually increasing. Okay, in that we can say zero-dimensional potential well, that is the example for quantum dot. One-dimensional potential well, that is the quantum well we can call. Two-dimensional potential well, that is the quantum well. Okay, this is about the particularly two factors that will affect the properties of the nanoparticles. Okay, right. We are closing this session.